So now the new lecture for today doesn't work. Here we go. Is on packaging and housing concepts. So that's probably something the hardcore engineers of you might have heard in their engineering programs, and the hardcore neuroscientists might get a little bit afraid what's coming now. This is here a kind of focus on a very special subset. And if you don't mind, I would leave the blinds down and we have probably more contrast here. So packaging and housing is one of the key issues for invasive medical devices. We have seen the pill there, which travels once through the human body, and that means we have to protect the pill from the fluids of the human body. And we have to protect the human body from all the leakages and residues that might come out of those technical agents that we have. And there are certain concepts that I like to introduce today. Like to try to give you an idea what is this all about, and then focus more on the microsystems aspects. So what happens if we like to make things small? What are challenges and what are potential solutions? So that's the plan for today. I like to start with a classical, so cardiac pacemaker stuff thing, and want to transfer the ideas then into smaller devices. Can we do that one by one, or do we have to think outside the box to get something new? And one of the issues that we should talk about is hermeticity. In reality, hermeticity is a kind of continuous thing. But to introduce that, I like to take a more digital concept. So either something is hermetic or it's not. I mean, it's being dead or being alive, being pregnant or being non-pregnant. There's hardly anything in between. There are transitions, but that's a different story. So, if we look in active implants in conventional technology, and I have to admit that these are neither the cutting edge photographs of last week, nor are all of those devices still on the market. But it gives us a nice overview how things look like. And most of those implants, might it be now permanent or like those imaging pills for a day or something like that, have a package. The longer they stay inside the body, the more massive the package is to be long-term stable somehow. And this is here the package, which houses batteries and the electronics. And we have then cables, wires leading to the part where interaction with the human body should take place. I want to focus on one thing a little bit more in detail. That was a beautiful approach. Looks a little bit like kind of Stone Age technology, but even it is quite old. I like to give you an insight what challenges are, and this is a good example to pinpoint the challenges there, and then it's up to you to take your imagination to make something cooler out of that. Yeah. This was all about watertight packages, and water and gas tight in technical terms is called hermetic. But it's stiff. A piece of titanium, a piece of ceramic is really stiff. And people say, well, the body is not that stiff, the body is more flexible, our eye, our muscles, our nerves, that's more like, well, not jelly, but not as hard as ceramics. Can't we make a flexible transition there? And a lot of persons used materials, mainly polymers. Might it be perylene C, might it be in silicone rubber around. And in some cases, if you talk to persons who are using that as implanting that, they are not very well aware why those things survive. They have their own imagination, and this is sometimes a bit different from what's really happening. Therefore, please take care that you, as somebody with some education in engineering, knows that silicone rubber, for example, is permeable for water vapor. Yeah, I mean, if you look into your bathtub or in your shower, it gets wet and the water diffuses and then it evaporates again, and if this takes long enough, then it's dry again, right? And after a certain time, it looks ugly, and if you ask an expert, they tell you, well, these silicone things in your shower and bathtub, they should be exchanged. That's good for your shower, that's not good for an implant. You cannot go in there and exchange the package, right? That's a bit difficult. And probably I can comment on those things a little bit later on today, how they work and what the thing is. So if we come to the material properties, if we look from a bird's eye perspective on the material properties, and I will ask you, how should those materials be for such a package? I think we could agree they should be mechanically robust. If the surgeon takes them in his or her hands, probably with tweezers, with all the instrumentation, the tools you have in a surgical theater, then they should be robust, that they don't get broken before they are implanted. They should have electrical insulators. So if you implant something with an electronic circuit in there, you don't want to have the body on the full battery potential. Not if it's not an implantable defibrillator, but then even then you want to know where the contact points are that you use. All the rest should be electrically insulated. There should a barrier against gases, water and ions in such a way that the electronic components neither get short-circuited nor do they corrode. And this is a thing. Short-circuit and corrosion, they're different mechanisms. If there is no water and no salt, it cannot corrode. I think this is what we can agree. If you put something in a desert and there's no water, no corrosion occurs. And the question always is, when does corrosion occur? And there are many theories there. And one theory says we need fluid water. And the question is, what is fluid water? If you come to the boundaries and to the limits, where does water vapor transfers into fluid water? And a common definition is you should have 3 monolayers of water to talk about fluid. That would mean if you prevent water from condensation, you could prevent corrosion, even though the material is not a barrier against it. And how can you do that? I mean, either you make a barrier, then water cannot penetrate, or you put something on your electronic circuit that sticks there so tight that the water cannot condensate. The effect is the same, your device survives, but the mechanisms are different. And that's one of the important take-home message. There are materials that are not hermetic, but if they stick well, I can prevent water from condensation, and then no corrosion occurs. This is really a tricky one. Normally, materials don't like to stick that much onto each other. If you have a bit of dirt, they stick even less. And a bit of dirt could be your fingerprint with a little bit of grease or proteins or dust. It could be a grain of salt that is left over from whatever washing cycle. And if this is not well done, then over time, not in a minute, but over time, this can lead to dissolution of the material. Then osmosis comes into game, right? So if you have a little bit of salt on one side and no salt on the other side, then osmosis drags water. If there's no room for the water to go, then it pushes to the insulation layer, and if the force of the osmosis is larger than the adhesion force, then it just pushes all your encapsulation away. It's not theoretically theory, it's practice that this happens. It's not, sometimes you have theory, you know, like those movies where whatever planet bumps into the Earth or whatever, that's one out of a million or even less, and here it's really something within days or within hours. If we need inductive coupling, so electromagnetic waves, we should be sure that the electromagnetic wave comes up to the receiver. Otherwise, if you make an electrical shield all over the place and you put a coil in, then it's probably not good for receiving energy. This is one of the really mean things in implants. If you have an active implant, in many cases you need a connection to the outside world, because you don't, in the imaging pill it's fine. You put a shell around everything. Even with that hemo pill, it's worse because you need. It's not worse because it's optically, and you can have something where the light shines through. But if you have electrical contacts, you need somehow a wire from the inner side of your package to the outside, and any feed through is a kind of a hole where water could penetrate, and therefore we have to take care to make those things really close. A good concept is a spark in the combustion engine. Zündkerze. I'm gone. A word, you know, if you have, I think it's a spark plug in a combustion engine, where you have to make that spark, that the fuel gets to an explosion. Yeah, that means it must be close, otherwise the whole motor would explode. But you need that electrical feed through from the outside to the inside to get that spark into your volume, and then to make it explode at the right point in time. That's good for a motor, and most motors nowadays have less than 12 cylinders. Most of ours now have 4. It means you just need 4 spark plugs. If you would have computer-brain interface, you would probably need 100 channels, so 100 spark plugs somewhere in an implant would be too space-consuming. That's always the question: how can I make that small? And I'll show you some examples. If we look on the components here, we have several, so sensors and actuators, cables, plugs, electronics. We've seen in the movie today, another important thing is the extracorporeal handheld user device with probably only 2 buttons, something that makes blink blink to show you it's working, and a screen with idiot-proof data management. Yeah. On the material side, I already said we need the mechanics to take into consideration, and of course the anatomy. Depending where this device goes, we have to meet boundary conditions that the device is small enough. And people tried over the last, 50 years to think about modularity of systems, that you could exchange modules or components. There are few things that have been established, but all in all, it's really hard to get a high level of modularity. We can probably agree on certain connector concepts, but that comes with a price that they are relatively bulky and of low complexity. If we talk about packages, this is the most important graph ever. And it comes in many versions. So this is about the permeability of materials for water vapor on the x-axis and the thickness of those materials on the y-axis. On the left y-axis, this is a logarithmic scale, and this logarithmic scale is translated into a metric scale on the right-hand side. And the permeability in grams of water per centimeter, seconds, and torr. It's really a very strange assembly of units. You can imagine the question behind the units is how much water vapor comes at a given pressure through a material of a certain thickness over a certain cross-sectional area. That's the question behind that. So how much water comes in? And that depends on the cross-sectional area. The larger the area is, the more can go through. The thicker the area is, the thicker the material is, the longer it takes. And the higher the pressure, the more driving force you have. If you have a pressure gradient from the outside to the inside and you have 2 bar, for example, or hectopascal or whatever unit pleases you most, then it pushes more than having a lower pressure there. So, and we have different materials here. Silicone rubbers, epoxies, fluorocarbons, glasses, ceramics, metals. And you will find silicone rubber as encapsulant for medical devices. And looking here, you would say, well, this is on the very left-hand side. And if we think on the definition of hermeticity, if water vapor comes in, it's bad. And the definition here is how long does it take until the inner side of a package has 50% of the water from the outside world. And you can describe that either as permeability, that is more that technical thing on the upper x-axis, and you can transfer that somehow in a given device of a given material and say, well, I look on my watch and look how long does it take until I have 50% on the inside. And that's the lower x-axis. And if I make a chronic implant, I would say I like to have it to survive for at least 10 years. Then I would go on the x-axis to my 10 years line and would draw a vertical line. And whatever is right of that is safe. And if we do that, we see that we are in the range where glasses, ceramics, and metals come into consideration. And then I would say, well, but I don't want to make it too thick. Probably the package wall should be less than 1 millimeter. And then you would go on the right-hand side y-axis to the millimeter scale and draw a horizontal line. And since I have no pen on my computer here, I'll have to trick it out. And that will mean if something should survive for 10 years and should be a maximum of 1 millimeter thick, only the materials in that rectangle can be used. And there's a little bit left of glasses, there are ceramics, and there are metals. That's a very pragmatic approach. If I go towards hermeticity, if I say I don't care of hermeticity and just want to make things stick to each other, then we can go on the upper left. but this is sometimes hard to negotiate with legal entities. They are sometimes not much willing to dive too deep into material science. They want to have something that is easy to argue. If you go into different textbooks, you might find that permeability is probably not in old style torr, but in hectopascal or whatever. So the factor might vary a little bit, but the general principle is the same. And the definition of leakage rate over time, so hermeticity is less than 10 to the power of minus 9 millibar liter per second. You have to know that this is then measured as an integral part. So you put a device into a machine and measure does gas leaks out, because you cannot measure water that good. And then you take helium, because helium is not that available in air. So if helium is there in your mass spectrometer, it must come from the package. Every device has its detection limit. And detection limits of helium leakage testers are about 10 to the minus 12 millibar liter per second. And that will mean you have to measure a certain time. There are international standards, and if you go below 1 centimeter cubic of the package volume, you come in that particular standard that is binding in the US. It's a military standard, to funny things like you have to place your device first for 30 days into an environment with helium, that the helium can creep in if there are some holes in there. And then you have to measure for 10 or 12 days if the helium comes out. If you would do that for every device you produce, you manufacture, that will mean every device that should be sold should go for 30 days in tests, just if it's tight or not, if it's watertight. And this is something that is not feasible for manufacturing. If you think that you make whatever 100 pieces or 1,000 pieces per day, then you would need 1,000 of those very expensive machines in parallel. And this is currently under discussion, if you really have to do something like that, or if different approaches could be also feasible. And one approach that is currently under investigation is a kind of condition monitoring. Means you measure with whatever humidity sensor inside a package, how much humidity do I have, and is this still good enough? Just to give you an example where things like that could go, there has been a product launched on the market which is called the Alpha Pump. The Alpha Pump is a product for persons suffering from liver cirrhosis, so end stage, if you have drunk your life much too much, then the liver does not work any longer in a proper manner, and it secretes water in the belly. That means those persons get a huge belly. And they have in their end stage life expectancy of less than 2 years. And this company produced a pump where you pump up the water that is secreted and pump it somewhere else where it gets drained in the body. I said, well, this is a life expectancy of the patients of 2 years. So we make a device encapsulated into epoxy resin. I know that from the hardware store. Endfest, for example. So I'll take an epoxy and encapsulate everything and prove that it works for 2 years, because they die earlier. And having that, and having the secretion of the water outside the body, their life expectancy rose. So their life expectancy was, after using that implant, now 3 or 4 years. And that was a tricky thing for the company, because they got approval for 2 years. And what do you do if you get approval for 2 years and your patients live longer? I mean, that's good for the patients, but if you are a lawyer, you don't think about the patients, you just think about the legal boundary conditions. And that means, and sounds funny, but it's sometimes there are really strange things with that. There are other things where that don't go into those storytelling. But this is one of the outcomes when the medical device regulation in Europe was revised, is now that you have to put all that knowledge that you get in an annual review of your device. And if things change, you have to renew or optimize or re-undergo your risk assessment and risk management, and have to, at any case where something is really serious, you have to change the whole procedure, the device, the documentation, all the assessment that you did. So there was one thing now with the materials and the thickness. If I want to get an implant that I get now, and my life expectancy is hopefully another 25 or 30 years, I want to be sure that this device lives that long. Or at least I want to get a certificate that tells me this device lives for 10 years, right? If I would be the manufacturer, I would have to prove that. But I don't want to test every device 10 years. Or if I claim it lasts for 30 years, I don't want to test my devices 30 years to say, hey, they are safe. Then I'm completely bankrupt if I would test every device 30 years. So what can I do to test it shorter and still give that certificate that it lives longer? And the idea behind that is accelerated aging. Accelerated aging means we have processes that are diffusion driven. And if you have diffusion, temperature is your friend or your enemy, depending how you take it. And this is called a first order process. So that means we have an equation where we have k as the value, and this is equal to factor a multiplied with an exponential function, and we have the activation energy and the temperature, and k is a Boltzmann's constant. That means the larger the E is, or the T, the E is dependent on the T, and that means if I make things warmer, they see more energy and they fail faster. Yeah, if I make something, I have no good example from daily life. I stay away from that. So you have to believe me. If you make it warmer, it fails faster. Boundary condition, which I already said, but sometimes people just keep in mind, the warmer I make it, the faster it goes, and then you can come to the idea, well, then I make it really warm, then it goes really fast. Theoretically, yes, but we have to prove that it's still a first order process, right? If I do something, I should take care that I don't destroy the material by heating it up. And this is especially important with polymers. We're talking here about dead materials. I mean, you know that all. If you want to cook something, you cannot cook it 3 days by 22 degrees C, then it's never cooked. So you have to go over a certain threshold. Here, we are not allowed to exceed that threshold. So it must be still according to that equation. If we are in those boundary conditions, and in polymers is less 60 degrees C is a kind of rule of thumb. We should not go above 60 degrees C in polymers. In semiconductor materials or ceramics or metals, we can go up to 90. Above 90, it's a bit critical, since we do not want to have our water being boiled. And if we have that, we can use the equation, say, well, if it fails at 90 degrees C within 14 days, at 80 degrees C it fails over 35 days, or after 35 days. With that, we get the activation energy out of that, and we can predict that the mean time to failure, MTTF, mean time to failure, at 37 degrees, so body temperature, would be 9 years. That estimation of the activation energy is the main cause of failure. If you slightly are beyond the real number, that is easily a factor of 5 or 10. The rule of thumb that you find in many applications is plus 10 degrees means twice the failure rates. Yeah, so 20 degrees would be then 4 times the time, mean time to failure. That is the rule of thumb that is quite often used, but you should be a bit suspicious, especially if your mean time to failure comes out as 10,000 years or something like that. Then you can be sure that this is a very rough estimation and the reality might be worse than that. So we had in our own experiments, we had mean time to failures due to that estimation of about 1,200 years or something like that, and things were gone after 3 years. Not even close, right? So, and the models, and you just need that. The others are, there are plenty models from different persons over the years said, well, we should slightly modify the factor or put another exponent somewhere, or consider something in a different manner, or take a certain activation energy, or whatever. Take-home message is it's really difficult. But there's no better method. That's the other thing. You might ask me, why do people such a stupid stuff if it doesn't work? And the answer is, they would love to do it in a different manner, but there's no alternative. So you still have to tweak around with the parameters there and see how far you can go. So the implant concepts are, as I tried to derive from that graph, metal, ceramics, glass. As metal, we use titanium. Titanium has the beauty that it's not that heavy, that it's tough, that we can borrow a lot of experience from aerospace. And the most important thing, it comes with a native oxide. So if you have titanium and you make a scratch into that, you have bare titanium, and just seeing the ambient oxygen, titanium makes an oxide and closes that. That's the beauty. It's the same what happens in standard iron. But we all know if we put iron outside in the rain, it's not that stable. And the difference between iron and titanium is that titanium, the volume of titanium oxide is closer to the volume of titanium than iron oxide is to iron. And if that volume is, the volume ratio is between 1 and 2, then it stays stable. If it's larger, it flakes off, as we all know from iron. We get rust, and the rust flakes off, then we have back again bare iron, it rusts, and if we wait long enough, it's gone away. In titanium, that ratio is close to each other, and therefore it's a kind of self-healing material. That's the beauty there. However, metal, it attenuates electromagnetic waves quite well. If we do not have much to talk, like in a cardiac pacemaker, so what do we have to talk? We probably ask the cardiac pacemaker, hey, how are you? How full is your battery? Then we can take a stronger extracorporeal field, and if we don't get a good response, we can ask twice or 3 times. If we have a cochlear implant where you want to listen in real time, this is probably a bad idea. So the data rate is much higher, and you cannot afford that you resend data 2, 3, 4, 5, 6 times. Therefore, in those cases where you really need a fast and continuous and strong exchange of data and probably energy, the coil is placed outside of the package. And as we see on the upper row for the cochlear implant, the right-hand side part is the coil embedded into silicone rubber, and we have a magnet in the middle that we can stick a coil from the outside. That's on one hand good because you don't have to hold your outside coil, and it's a self-alignment. The coil is always in the right position. You might have seen that here in town, people with cochlear implants. If not, just open your eyes and have a look if you walk through the city. Since we have a relatively large cochlear implant center, you might see some of them, especially around the station when they come in from the outskirts, with their coil behind the ear. Yeah, so that's all to say to that slide. As alternative, we can use ceramic packages, alumina, so aluminum oxide, Al2O3. It's very tight. It's a bit challenging to connect that to metal. So there are some established procedures that you get the metal deposited on the aluminum oxide that helps you to then weld the package close. The only downside of ceramics is that this is a very brittle material. And that was one of the major criticisms from the early days on. People say, well, if you have a material like ceramics, you have to prove that it doesn't break if you have an accident. And then you have to define what is the severity of the accident and what does that mean. I mean, if the accident is so severe that you are dead before, at the same time where the package breaks, then you can probably argue that we're against the legal entity. They say, well, it doesn't matter. If I'm already dead, I don't need a functioning implant. That sounds harsh, but this is the way how those negotiations go. Or you could say, well, in most cases it doesn't break, and I don't know if I have that. No, I don't have it with me. The old standard was cochlear implants. You might have heard that cochlear implants have established in France, in the US, and in Australia. And Australia is part of the Commonwealth, and all former Commonwealth nations are really addicted to baseball and softball playing. And that means they found out, well, what could be the worst accident I can imagine in those days, 1980, 1985, and that was a young boy trying to learn softball playing, standing there with a bat, waiting for the ball to come, not hitting the ball, but the ball hits you behind the ear where the implant is. That is an impact of 2 joules. And so there is still a hammer test where you take a hammer. We have something in our labs. You put it and you bump it with 2 joules onto your package. And you are allowed to put an intermediate layer of artificial skin, which is a piece of silicone rubber in between. Unfortunately, people found out, well, softball playing is no longer that thing what people do, but they go bicycling. And if you fall from your bicycle, then it's an impact of 4 joules. I mean, it's twice the value. And 4 joules is really a thing. So I have old movies where we try to make our first ceramic packages stable, and what we have seen was a huge mess, because that 2 joule hammer is really strong, and we destroyed a lot of packages by bumping that hammer into our packages. So 2 joule is doable, 4 joule is really a challenge for ceramic packages. Probably you can argue something. Yeah, they say, well, this is really rare, and we do some condition monitoring, and you have an accident, and it's not a life-saving implant, then you could exchange it or something like that. But this should be taken into account in your risk management procedure when it comes to the risks that might occur and you have to consider in device design. What you can see here in the lower picture is that we have the package on the left-hand side, and on the right-hand side we have a lid, and this lid contains the feed-throughs. And the question is, how do feed-throughs look like? And this is not the place here where I like to go with you in all the secrets of interfaces of feed-throughs, but just as an overview, we take a ring that can be welded into the lid, and then we have the pins going through. And the pins can be either with a glass sealing, so you melt a glass pearl around a conductive pin, and then by selecting in a proper manner the glass and the pin and the ring around, you get either a purely chemical connection there, so in best case with high binding energies, or you get a combination of a chemical bonding with a compression seal. That means you choose your thing such that the ring around has a larger thermal coefficient of expansion than the glass. You make it warm, you put it together, and when it cools down, it presses from the outside on the glass and on the pin. This is one option. The other option to glass, the alternative to metal glass feed-throughs are metal ceramic feed-throughs, where you solder or you braze. Braze means soldering at higher temperatures. You braze the pin into the feed-through, as shown here. Ceramics, metal pins, metallization on the ceramic, and then you braze the pins inside. The density per unit area is relatively limited, and that is one of the current limitations. There are two famous companies for medical device components. One is Schott, the other is Heraeus. They have worked on higher integration densities there. I believe that Schott has a product out on the market. Heraeus still, to my best knowledge, does not have the process finished there. But that means this is one of the things, especially if we talk about those brain-computer interfaces, high channel counts. This is one of the showstoppers here. And it's huge. And if we have a feed-through, that does not mean that we already have something connected, so we would need cables and connectors to that. And most of those cables and connectors are derived from pacemaker industry. We already have those cardiac pacemakers here, so we don't need too many contacts there. That's the beauty. And therefore, cables and connectors could be relatively simple. But it's limiting in the number of wires. Cracks connectors have been an alternative at points in time from the mid-70s on, where the cardiac pacemaker cable still had one contact. It was not that much, and Cracks connectors came with 3 of them. So helically wound cables with 3 independent lines that go in 3 pins, and they were smaller than the other things around. The company is still around. Fintech Medical in the UK, a very small company. Don't know if they have 3 or 5 employees or 10 or something like that, but really small, very customer design. This is really Cooper. This is not copper. This is Cooper. That's the name of the guy who invented the cable. Yeah, if we now want to make things smaller and more complex, we probably need different technologies. We cannot take cardiac pacemaker technology and scale it up to 1,000 contacts, or not even to 100 contacts. That would be too bulky. And therefore the idea is to take, why not using or trying to use those methods that we have around. Make things smaller on one hand, and I come to that slide in a second, and use technologies from microelectronics. And one thing to start with was make things more modular. So don't take a piece of titanium, grind a case out of that and put something in. Why can't we use those techniques that we use from electronics assembly? And that was mainly done in the UK with father and son Donaldson. They had the idea, if we print for harsh environments, high temperatures, chemical harsh environments, if we print circuit boards on ceramics, why can't we do that for implants? So make a printed circuit board, put all the components on there, encapsulate them, at least with a protective varnish, that no other stuff comes on, and then assemble a ring around that. So we have alumina base plate, we take a ring around and an alumina top plate, and then we have to dry it and close it. And then we have an hermetic package. Isn't that cool? And they did that here. This is here the base plate, intermediate epoxy first to glue that together, that it doesn't fall apart before you solder it together. The ring as spacer and the lid, and then a final seal. And this is how it looks like at the very end. If everything is assembled, we still have the hole here. We have the feed-throughs in the base plate. We have the hole, we can heat it up so all water vapor goes away, and then we can fill some helium in there for the leakage testing, and we can solder that shut. Check, done here. Similar thing, same group, can be also done if you take a metal cap instead of a ceramic cap. So you have a metal cap and your printed circuit board, and you bring it somehow together and solder it. Yeah?
A question to 2 slides back. Did they really use lead-based solder?
Yeah, they used lead-based solder. And lead-based solder is still one of the few exemptions in the RoHS and the REACH for medical implants. The reason for that is that the TG, the glass transition temperature, in lead-based solders is more stable than in non-lead-based solders. Part 1. Part 2, you can then argue, I use so little lead that the LD50, the lethal dose, would be so much that you have to get 300 years and the implant must be that. That's always a situation where people say, I don't feel very comfortable, even if it's a little. But those things do not get implanted as they are here. That means they get an additional packaging, and that is the trick. If you do a packaging with silicone rubber has a very, very, very slow diffusion rate for anything else but water vapor. Very little with respect to ions, and very, very, very little with respect to heavy metal ions. That means if you do that well, you have no leakage of lead into the body. This is, of course, hard to discuss in those days. I mean, they did it they started in the 60s. And RoHS came around 2000, where that risk of hazardous substances where lead was banned out of solder. Also, those pastes for screen printing had a lot of lead, and all the work was done by the Donaldsons to prove that this is stable. And we here redid it around 2000 to show that the lead-free pastes are also stable. So it's changing, but it was one of the last exemptions to use lead because of the reliability. And the delta T, so the temperature difference between soldering and destruction temperatures and diffusion related processes is smaller in most of the lead-free solders. And that means you have to play some tricks. Which one do I use? I mean, we have a lot of silver in the others, in the new ones, indium, tin, silver, and they all tend to love dendrite formation. That means if you solder and you have a little bit of ions and a voltage gradient, they form structures like in between crystals and Christmas trees. And by that they can have a lateral outgrowth that short circuits adjacent lines. And that means you have to check out what voltages am I allowed to apply, how clean must it be that dendrite growth is prohibited. That means it's reinventing the wheel again with the new classes of lead-free solders and pastes. So that was quite challenging there. But you're right, yeah, that's all with lead. Standard PBSN 5446. So what about non-hermetic encapsulation? So something where water vapor can get through. Already said it must stick like hell to be stable. We have silicone rubber as material class and Parylene C. Silicone rubbers are the most favorite materials for that, even though they got a little bit bad reputation some years ago, and the last, well, it comes every 10 years or something like that, that companies who manufacture breast implants do something that they should not do. The first one was Dow Corning in the 1970s or 80s, and then they gave up delivering medical silicone rubbers, and the last one was the PIP scandal around 2010-ish or something like that, where a lot of breast implants broke and released fluid, jelly, silicone rubber into the bodies. The thing was that this is not due to the fact that silicone rubber is a bad material, but it was just criminal energy. Those guys in France bought hardware store silicone rubber because it was cheaper than the medical grade one, and they had an audit from TÜV Süd, and they changed the material while the guys were entering the ground floor. They changed the material in the first floor back to medical grade material. So that was not missing regulation or whatever, it was pure criminal energy. And this is something we should keep in mind. If we use the materials properly, and with encapsulation of implants, I mean some gram and not 2 pounds, then it's safe, and we have to know which material we use. And I was really astonished. Two of my PhD students wrote a report on something. I said, well, we cannot hand that report in. It sounds a bit stupid. You did something and the silicone rubber remains sticky. That's well known. These are if you take the wrong gloves with certain silicone rubbers, you have sulfur in there, and sulfur prevents proper vulcanization of silicone rubber. That's well known. They said, well, we have talked to some other groups, they did not believe us. Okay, so keep it in the report. So there are things where silicone rubber doesn't work well. But this is a kind of state-of-the-art knowledge. Yeah? You just have to go into your leaflets of the material and read to the very last page, and then they tell you what to do and what not to do. And this is my take-home message here. You have to do it properly, and then it works. Parylene C is a kind of that magic material that can do everything. It's a really good material, but we have to check out what can we do with Parylene C and where are the limitations, as with every material. And it was, Parylene C was invented in, the famous Gorham process has been published in 1968 or 66, that range. And it was already as medical grade material taken into the USA, United States Pharmacopoeia. That's a database where medical grade materials are listed. And the reason for that is, my very personal opinion, is not that it was so good, but it was that point in time where cardiac pacemakers were made out of epoxy. And the epoxy was not very pure, and if you look up old literature in databases, which is now digitized, from the 70s you find something like pacemaker dermatitis. That means there was skin erosion at that place where the pacemaker was implanted. And the reason for that was that the epoxy had toxic leakage agents that came out and destroyed the skin. And Parylene C was an awesome material. You could coat your epoxy pacemaker with Parylene C, and by that you prevented the leakage of toxic agents into the body. That's called intelligent house. So, I don't complain about Parylene C, but I think if we know why this has been transferred so fast into such a database, it was the need. And if we use it for something different, we should check up, does it meet our requirements that we have? So this is what I told you now 3 times in written words. Keep moisture out, or use silicone rubber, and then you get moisture. But it doesn't matter if you get moisture if things stick together. Then it works. But this is still a non-hermetic encapsulation. And if some colleague tells you that they run a company with the only hermetic silicone rubber worldwide, you are allowed to doubt that they understood the basic principles. Yeah, I had it once and I gave up. Yeah, I really gave up because they said we have waterproof hermetic silicone rubber, and then I asked which one is that, and they told me the number. And it's not. Yeah, but our things work. And I said, yeah, of course they work, because this silicone rubber sticks so well to everything that water has no chance to condensate. And that's the reason why your product survives. No, it's hermetic. We did something. It's okay. Let's talk about different things. This is how it could look like. There was a kind of case study where I was involved, and I wanted to see, are we stable enough that a simple system can survive for certain weeks and months. So we did a one-channel stimulator, which is not very popular if you just come with one channel. But it was not the proof that we can make one channel, but the reason behind that was to investigate in vivo the stability of the coating and the packaging. And that was a combination of Parylene C and silicone rubber, and it worked up to 3 months. And with that, already showed that to you. That process was further developed for vision prosthesis implants. If we go over the last minutes now to hermetic encapsulation of miniaturized systems, we have to check out how can we use those ceramics, metals, whatever, in combination with microelectronics manufacturing techniques. And if we look, and this is a combination between hermetic and non-hermetic materials, the question quite often is what can we use as insulator there? We find out that we come to the usual suspects. Usual suspects mean with respect to silicon technology, electronics manufacturing, it's silicon oxide and silicon nitride as the 2 materials that we can use in manufacturing fabs. We have polyimide as material, well introduced in electronics manufacturing in the 1970s. We have metals, and we have Parylene C. And in many cases, if we look up the materials, we should look up the methods to work with the materials in parallel. So if I would say silicon dioxide, I would have a single crystal orientation in mind that is different from something where I have silicon and oxide, but it's a wild mixture of materials and not in a crystalline phase. So we always have to check a little bit, is it crystalline, is it amorphous, do we have other agents in there from the manufacturing process. And here are some equations, and we have to use them with care. And that was I was sitting over a coffee with a colleague of mine, and then he had, I don't believe that, from the fundamental science that could not work. And then we took out that paper that is cited here and said, look, there's another paper where they say they claim that this works. Okay, and then we were really getting warm, and we took the other paper, and in the other paper there was already a kind of restriction that, yeah, it can happen if you have lousy materials, but the basic mechanisms are published there. And then we were, I guess, in 1957 back, and this paper does not exist. Took us the whole afternoon. Yeah, took us the whole afternoon. We found, we were really lucky that that journal was digitized back to 1930 or something like that. And that volume existed, but that paper did not exist in that volume, and the title of the paper did not exist in any of the volumes. So take care. There's another situation where people point to something, and that something was a classified paper in a Russian database that was once translated in German and was available for 9 months after the wall broke down, and it's still classified again and vanished somewhere. So really take care. There's sometimes some scientific rumors, people cite that, and if you write a review, you don't want to say that you did not read that paper, but just the review of your colleague who cited that paper, and then you're brave enough to cite that the original paper, and it can happen that rumors are spread over years into the whole community and then it's really hard, to say, well, I looked that really up, it doesn't exist. That's hard to get through. It was a little bit like that, but in general that works under the boundary conditions that we have not stoichiometric material, really crystalline, but that we have some residues from the process technology in there. And if we have, for example, here, a little bit of sodium and water in our silicon dioxide, then this might dissolve, and then we get silicon hydroxide, which is prone to get dissolved. Same if we have chloride here, we get some salts there. That means silicon is not really the most stable material. We can use that, but we have to take care. If it's a single crystal, it might work. If we have it deposited out of a gas phase where there has been a lot of hydrogen and whatever in the original gases, then we might have non-stoichiometric effects that are prone to dissolution. Same with silicon nitride. Silicon nitride, if we deposit that from the gas phase, is never stoichiometric. It doesn't matter in most cases, but if we believe that it's really stable, we have to take care. And this is the question of the binding energies. How good are the binding energies, and is the binding energy or the surface energy of another material better? And then it gets transferred. We can play some tricks. So here we get ammonium, which is water soluble, so the silicon goes away, and if we have non-stoichiometric silicon dioxide, we can go to silica, and silica is also water soluble. So just as a warning. Especially if we are in vivo, if we have foreign body reactions, and macrophages come and want to eat our material up. And a former colleague of mine did some tests on that. Macrophages can lower the pH value on a surface down to pH of 1. That's something. And that means if we have these foreign body reactions, the enzymes and cells can accelerate deterioration products there. One trick is to use multi-layers, and the trick in this case is not that, well, one trick is the thicker a material is, the longer it takes before it gets eaten up. That's one of the issues, and the thicker it is, the longer it takes for a molecule of water to diffuse through. But in many cases, we take those combinations of materials to get at the interfaces certain distortions of the energy bands. For those of you who have heard about the Fermi level in one of the more serious lectures, this is what happens here. So by putting silicon oxide and silicon nitride together, for example, the activation energy gets larger to destroy that material, since the Fermi levels gets distorted there at the interfaces. And this is good, but it's not, we always have to think twice if this is then really improving the whole material, but these combinations are a good step. How can we still stay small? And I stole all the following slides from a dear colleague of mine, Colin Najafi, who was here 2 or 3 times on a sabbatical. He's at University of Michigan in Ann Arbor. And this center there is amongst really the pioneers of packaging of microimplants. And they invented the Michigan probes, so those needles for the brain. And had some ideas, can we use several modalities on a single chip, accelerometers, gyros, a lab on a chip, electrical things, and the requirements getting larger and larger and more serious. If you do that, and they had the idea, can't we put a micro glass package on that? And the question then is twofold. One thing is it hermetic? And B, how to assemble that it really sticks. And there are many bonding techniques. And it was always funny, even with the experts in the field. There's theory and there's practice, and if things have to go small, they have to go fast and small, they say, come on, I take a little bit of plastic and put it in between. But if you take plastic, it's no longer hermetic, right? This is the basic statement. And if you have here, to get things together, plastic as glue, it might even act a little bit like a wick, so that it really sucks in all the fluid that you get and pumps it nicely into the inner side of the package. This is something you should not do at all. But the challenge here is, if you put something on top, where do I get my connections to the outside? That means we need, in this case of electronic circuits, lateral feed-throughs, since we have no technology to drill them vertically through the silicon chip. I mean, we could try, but it's easier to have them horizontally. And there are many microelectronic specific techniques to assemble that. We have then different options for package materials, could be glass ceramic or even silicon or thin metal films, and we have to check which feed-throughs do we need for what application. There's now optogenetics around, that means we need some optical waveguides or something that shines light through the package wall. Electrical feed-throughs, if we have fluidics, then it's getting really hard. So how to make a fluidic feed-through somewhere that you get some agents through. And they started with thin films, so having your device with electronics, and this is a simple idea, taking an insulating material on top, that you have no short circuits, and then putting a metal layer on top like a titanium package, but made out of thin films. You have to take care if your thin film has tiny little pinholes, water can go through. polymers like to store that water, and then you have a beautiful water storage case under your thin film package. That's where you have to take care. The good thing is you have really a thin additional layer on top, so it does not get too thick there. You can really put a cap, so something massive, silicon cap, glass cap on top of that, with a question how to get that connected, and that's either then silicon glass anodic bonding. Anodic bonding takes place under high voltages and high temperatures and need a very planar surface. That is one of the downsides. If it's not really planar, it doesn't stick very well. If you solder and something gets fluid, then it can even level out certain inhomogeneities of the surface. You can do some anodic bonding of glass here with the packages as shown before. Want to speed up a little bit, and then they took a chisel and try to remove it. And the good thing here is that this is a cohesion break. Means the adhesion interface between the package and the substrate stayed stable, and they completely destroyed the package wall. That is a good outcome in this case, because their solder link survived. They did some accelerated aging here, and with a mean time to failure of 177 years, this is a good result, but I would immediately get suspicious if I get something like that. That's too large to be true. And they wanted to make a new kind of cochlear implant, so more complex, smaller, whatever. And I always have to smile on those slides. Really excellent work from the electronics side, but I would doubt a little bit that a medical doctor likes those sharp edges and corners off of the package wall. So this is what I learned. If you have something like that, you should put it in something more round, that surgeons are happy with you and don't see the edges and corners. That was then here, that package, really small on the fingertip there, was combined with polyimide interconnect lines and a small silicon-based front-end array to prove how miniaturization could work. But at the very end, it never made it into product. So they proved all the technologies, it could work, but you would need a company who's loving to do that, and probably another $300 million and 10 years to transfer that into a company. And the question is, would your performance be then so much better than all the other cochlear implants that somebody wants to get it? Yeah? If you are smaller, that's nice, but what's the advantage? The advantage must be in better hearing perception, in better voice discrimination, probably even in being able to understand tonal languages. That is still one of the challenges in cochlear implants. If you have something harsh like English or German, then it's fine, but Chinese with different tones at the beginning and the ending having different meanings, that's still a huge challenge in those cochlear implants, that you get those tonal things being well coded and transmitted. Yeah, we could go now into the very details of assembling and packaging techniques. Just an example here. If you have eutectic solder, that means a solder where the melting point of both components here, silicon and gold, is lower than the melting point of the single materials. Then you can melt something, and if you put a glass on top, it planarizes all the surface topology. That is good in soldering. There are other planarization steps where you can make it planar if you need that, but that always means you have to do steps that are not done in standard microelectronics processing. And this means you cannot order that at a fab. You have to do that at home in your own laboratory. They would throw you out immediately if you come to them with the idea, can't we do that? No. Their answer is always no. If you put gold into an electronics manufacturing line, you can, best thing is to burn the whole fab down. This gold diffuses into your electronic components and has a lifetime doping, so it sits down immediately at the Fermi level in the band gap, and with that all of your transfer behavior of electronic circuits is completely distorted. So this is your kind of marketing slide. If you want to encapsulate or package on the right-hand side the electronics being on that rectangular thing, you can either do can take polymers, then polydiamond on top as hermetic coating, and gold plating. That's shown here in more details how to do that. And the mean time to failure drops significantly down. I mean, they predict here a lifetime of 160 years. Good luck. I mean, I haven't heard about any probe that was able, from the Michigan side, to record signals for more than, I don't know, they do it normally acutely, so some months. Buta array has up to 5 years, so it's not on the probe itself, it's about foreign body reactions, about cables, connectors, electronics on the back end side. So that's good to have that stability here, but it's not the thing that limits the lifetime at the very end. So here an early approach, early means 2004, of the Utah array. Can we get rid of the connectors and cables and have it all wirelessly with a beautiful platform just on the footprint of the array? That was the idea. So place everything on the backside of such an array, capacitors at the edge, some spaces at the edge, some ASICs and coils in the middle. There were some PhD theses that went into that, even with a lid around, so beautiful stuff. I've was really jealous seeing all the results in the early 2000s, but the yield, that means the outcome of that, was relatively low, and the lifetime at the end was not that good, because if you have so many manufacturing steps, a lot of things can go wrong in between the different steps, and it was not made in a way that you could transfer this beautiful idea into mass production. And therefore they ran a little bit out of money and out of time and decided to sell it again with cables on the back end side, and now did a step where they said, well, if we want to do it wirelessly, the first step is to put a wireless module on the head mount connector. That sounds stupid. If you already have a percutaneous connector, isn't that the worst thing? But you do not need then to have a computer and a thick cable, but you have kind of matchbox-like transmitter which you can connect, and then it's the first step. You can get experience with that, and from that experience shape the next round of implants, and I'm pretty sure they will pop up with that idea in 1, 2, 3 years from now. Yeah, so that was here, multi-level packaging, and the last thing, give me just 3 minutes, is that glass package. The beautiful thing is you can look through, but if you ask somebody about glass, everybody would tell you, glass breaks immediately. So the feeling towards glass is not the best one when it comes to implants. And the idea here was to put a one-channel stimulator in an injectable package that you can inject into muscles with a needle. So place it there, having a microchip in there that you can place several, so they could address up to 256 of them. So the idea to have a distributed network of implants where you can activate the different muscles and to control everything, let's say, with huge coils into a t-shirt, something like that. The idea came to the table in the mid-70s or early 80s, where putting sensors into t-shirts was not that fashion. You know, now if we talk about wearables, everybody has some ideas in mind. Those were the days where people, why should I do that? It was 20 years before the iPhone 1 came to the market. But they had good ideas. One was for incontinence, for example, that you can train your muscles of the sphincters while sitting on the toilet seat, having the other coil in the toilet seat. Somebody did not calculate well. People didn't like it because it was too warm on the toilet seat when they get powered. The other stuff was in the intermediate time after stroke, if you have hemiplegia after stroke, and you know that this is for 12 weeks or whatever, and you can retrain it, but due to disuse, muscles get weak, and the arm pulls downward, and you get problems with your shoulder capsule. And the idea was to put some those bions in there, stimulate and train the muscle and keep the arm up. At the very end, there were two showstoppers. One was the edge of the capsule, where there were breakages. And the other was that they did not read the letters well, and they had a transmission frequency that was unfortunately one of the secret transmission frequencies of the US Air Force. And that was a lawsuit about 22 years, 25 years, which was really a showstopper. That I think that broke the neck of that application. There was once a nice documentary in the IEEE journal, in the Pulse, about Joe Schulman, who did that. And at the end, he won the lawsuit, but that was after 25 years. So take-home message: read the papers well and check twice if the frequency you're about to use is free. I still love that approach because it's very, very integrated and simple from idea. So, but the packaging is very complex. You needed here two different types of lasers: a YAG laser from one side and a CO2 laser for the other side, and a lot of hand work to assemble that stuff, put it together, and weld all the components together here. So that was something that could work, but was too complex to get transferred into mass production. So really a lot of things like putting one piece out on the other piece, taking your fingers off, shooting with a laser there, could be probably done with the help of assembly robots nowadays, but I think would be also good to revisit the design and make it less failure prone. So, and with that, like to summarize, we have challenges the more complex implants get. We have challenges the longer the implantation period is, from both package and electronics. And in nowadays where MR imaging is state of the art, we have to take care that our devices are at least MR conditional. That means they can be used under certain circumstances. What's still open is the question about high channel cables and high channel connectors and plugs. If you would say, let's make it all wireless, so a network of implants, we still have that challenge if this implant is in contact with the nervous system over an electrical modality, that we need some feed-throughs, and the feed-throughs have to be connected to your array or whatever, so we can shift it to another place, but the general challenge is still there about packaging and assembly and connecting things. And of course, the energy supply is not yet solved. We're still not yet there to have networks of implants, which could be useful. At least, and this is my strong belief, if we get older and those implants get more widespread, we might have a cochlear implant and a cardiac pacemaker and I don't know what else. It would be clever if those implants could at least talk to each other, that they know that the other is there. If it comes to, for example, artifact suppression or something like that, that you know this is the artifact from the cardiac pacemaker, it's always there, I don't care. Something like that you have that network stuff. A lot of persons started with a lot of enthusiasm about energy harvesting in implants. That would be beautiful if we could use blood glucose to drive our implants, for example, or movement. I think there are some options where you could use that. I would not sleep well if I would have to design an implant without any additional power source from safety aspects. So I would say we can probably combine that. So having a rechargeable battery where you can prolong the lifetime of the battery by energy harvesting, for example, something like that. I think we had now in the hype cycle, so the hype is over. We are in the well of disillusion, and now we have to see what can we bring together to make things work. And a lot of persons think about mimicking biological surfaces to make implants better. That's a cool research area. We still have a long way to go to understand what's really happening there. And with that, I'm really at the end. Here some research papers that I cited there. For you, the take-home messages, you have to select adequate materials, but that's not all. You have to check adhesion, and you should consider also the leakage between contacts. It's not only the leakage inside and outside of the package. If we have some adjacent lines, if they short-circuit each other's, that's also nothing we want to have. And the devil is in the detail. That's probably the best summary here for all the assembly and the materials and bring things together. That's now really the end. Thank you very much. I'll promise to upload everything now. Was a bit busy last week. Wish you a nice day, nice week, and hope to see you again next Monday here. Thank you very much.